All right, so looking at number 12,
Oh,
we start out with this, with NBS, and then heat. Or you could use peroxides, but if you see MBS, MBS should tip you off to what you're going to form. Nope. MBS is a allylic. Now be careful, because what somebody's going to try to do is, it's only for allylic CHs. Notice how this carbon is allylic, but are there any CHs on this carbon?
No.
There are no CHs on that allylic carbon. So, allylic is the one, so this is the pi bond.
Yep.
The allylic carbon is the one right next to the pi bond.
Okay.
So there's both allylic carbons. But it has to be an H. So there's no H, we can't ever have that one, so we actually have the radical form right there. So now you could draw a resonance structure here, but there's really no reason to, because it won't make it more stable or different, right? You'd make essentially a secondary radical again. All right, so let's take a look. If I do a resonance form here, I now have the pi bond here and the dot here. All right, so that's possible. So if I pull this up a little bit, so the product that would have resulted from this would be the bromine down here, right? The product for this one would have the bromine right here, right? So both these products are possible. But only one matters. So if you read this carefully, it's really only this one that matters. So let's read what the question says. So the question says, provide the major product, right? So only one, so we know we can make these two. There doesn't appear to be a preference for them. For the following reactions, it says omit byproducts, ignore stereochemistry. That's nice. Hint, if more than one product is possible, there are more than one product that is possible. Draw only the one that fits in the context of this two-step scheme. So the second reaction here is reacting with T-butoxide. Right, which of course is a big, bulky, strong base that does what kind of reactions? E2. So you should notice, right, you need to have what kind of hydrogens do an E2? Beta. And the beta hydrogens can't be on what? There's a beta hydrogen here, but it's an sp2ch. No good. So there's no way I can do an elimination with this. So essentially, this would be no reaction. Right, so that's what they're saying, omit, if there's more than one product as possible, draw only the one that fits in the context of this two-step scheme. So even though this is possible, this doesn't lead to anything for that second step. A little tricky. See that? Whereas this other one, A, there is a beta hydrogen that's reactive. And we can do the E2 reaction. And what do we make? And not just, we make a double bond, but look what, we made a conjugated double bond too.
Yeah.
Nice. So that's what we're trying to get to there. So the tricky part was, yes, you do make two possible products, A and B here. Right? Because you make two different intermediates because of resonance structures. But for the second step, I can't do an E2 with B because there's no beta hydrogens that are actually available. That's the trick. Yep.
So I missed NBS today. Do you want us to know the mechanism between?
Yep. So how MBS works? It gives you Br dot in small amounts.
Small amounts.
Yep. So the Br dot originally took the H off of here and made HBr,
Yeah,
and made that dot.
it left a dot. Okay.
Yep, and then NBS reacts with HBr itself and makes Br2, and that's what ends up reacting here.
Okay.
So that's in our class notes
The
too.
NBS never actually acts on
The NBS itself never actually touches this
the.
necessarily. For this one, we start off with cyclopentane. We need to make 3-bromocyclopentene. So that would be cyclopentene 1, 2, 3-bromocyclopentene. Alright? So we gotta figure out how to make this. So retrosynthetic analysis, we gotta work backwards. Do we add any carbons?
No.
Nope, didn't add any carbons, so that's good. So if we go one step back,
NBS. ROR.
So that- NBS is the reagent, but what's the star material gonna be?
Just,
Just what?
Oh, without
just the cycle.
Just the cyclopentene,
And
right? Good.
T.
Just cyclopentene,
Oh, what?
right? Going one step, just the star material. We'll get the reagents in a second. If I wanted to make cyclopentene, how do I add one pi bond? What do I need to have there?
Beta, or just a turbioxide.
A B, nope, that's a,
Just beta hydrogen.
well, I do need to have beta hydrogens, I do need to have turbioxide,
Just simple
and I need this,
bromine on it.
yep, this with a bromine.
Yeah.
Right? All those things will come along. And now we've learned, right? We've learned ways to add a bromine, take a CH and turn it into a bromine now, right? So we know how to add bromines now. So what reagents do we use to add just a bromine?
HBr.
BR2?
BR2, and we have to say light, right? We have to use the HV,
Yeah, HB.
right? Good. If I want to do an elimination, what do I need to do?
Beta hydrogens with.
Big bulky base,
Yes.
right? Beta hydrogens, good. And this, you'll notice this is symmetrical, so it can go either way. That's very good. And now, if I want to add a bromine in the allylic position, what do I use?
NBS?
NBS. And you can either use light or you can actually use peroxides there too.
Oh my gosh.
There you go. So looking at number 6. So 6 has this allyl group plus HBr, and they say peroxide, so I'm going to draw a generic peroxide. And they're telling us it's leading to this. So let's number our carbons. 1, 2, 3, 1, 2, 3. So you look at this, you should automatically see the bromine ends up on the left substituted carbon, so that should make you think anti-Markovnikov, right?
Yep.
So they want to know, you got to sort out the mechanisms for these. So let's see. First we got to do the mechanism. So the first step in any radical reaction is a initiation. So in this one, when you have peroxides around, that's the weakest bond. The OO bond is the weakest bond.
Did you say the ROOR, we should automatically think anti-Markovnikov?
Yes. That's peroxides. So the first step, we have our fishhook arrows, and we turn ROOR
RO times
2 RO dots. Now that's not the initiation, that's not the only initiation step. Because in our final product, what are we actually adding? A bromine. We're not adding RO dot, right? So we're not done initiating until we actually get the thing we want to add ready to go. So the next step, we take one of those RO dots, and what do you think it's going to react with? What's the next weakest bond?
Bromine.
Not just bromine, the HBr, yep. So let's have those two guys. So we'll make an alcohol, and we'll actually make Br dot, which is actually the species, right? Now we know the initiation is done. So the initiation actually has 2 steps here. So we have ROH plus Br dot. So that's the first 2 steps of our initiation. Right? Because until we make the Br dot, which ends up actually on the products, we're not done initiating. Now, the other steps, Propagation just means, right, we make another radical. Right? Initiation, right, usually means you don't start with any radicals at all, or it's the way they make the reactive species, but propagation is how these guys are going to react with each other. So in a propagation step, our alkene is going to react with our Br dot. 1, 2, 3. So where do you think the bromine's got, when you know the bromine ends up where? On 3, right? And why does it end up on 3 and not 2? But why is it anti-mark?
Well, because of,
Not resonance.
it's more stable.
What's more stable?
The radical is
On the secondary carbon, right? The radical is more stable on a secondary carbon than it is on a primary. Right? Hyperconjugation. Alright, so that's a propagation step. Anytime you make a new radical, that's a propagation step. Except for this step right here, because right, again, this is a different kind of thing. We're not done initiating until we have our Br dot, essentially. So this is a propagation step. There's a couple other ones you could do, of course. As long as you make another radical, you're good to go. And then a termination step is anytime two radicals come together and there is not a new radical formed. So that could be something simple like this. Imagine two BRs coming together, two BR dots. But the whole point is, in a termination, you're done. There's no new radicals. So there's lots of ways you could do this too. You get lots of complicated products. Right? The biggest thing was, just because it's a termination step doesn't mean it's the product forming step. People think termination means that's the step the product is formed, and that's not necessarily the case. It can be, but it doesn't have to be. So yeah, the biggest thing is, I've only shown one example of a termination, but for this problem, every single reaction needs to go into one of these three categories. Right? Initiation, propagation, and termination. Right? This is just one example. Right? This is all of the initiation. But I've just shown one propagation. And I've shown one termination. Right? So everybody needs to be in a bin. All right, working on number 9.
13, okay. Just going with the
It's in Cl2, low concentration. I want to know what are the major products for this reaction. So Cl2 is pretty reactive, remember that? So Br2, so Cl2 doesn't even need the light at this point. I guess there's probably light in here. But what's it going to do? Right, so Br2 in light would do what? What would it take off? Would it do addition or substitution?
Wait, what if mine doesn't say light, it just says low concentration?
Low concentration, same idea. So
Well,
it's
substitution?
it'll do substitution. Where's it going to do a substitution at? So it's going to take an H off. So we're going to end up with an allylic radical.
Did you say the Cl2HB, it does what?
It takes off the allylic radical, allylic CH, so it makes an allylic radical. So it's just like the Br2 when I showed you guys earlier today. All right, so you get an allylic radical like this. Here's the issue. Okay, so there's one, right? You can imagine this reacts with Cl dot. Oh, happy day. There's one product. That's easy to see, all right? That's for sure one of the products. But there's actually going to be 3 total products here. So there's one. That's the easiest one to see. I'm going to redraw this intermediate. So this is the same. I'm just going to redraw it because we're going to do a resonance structure on this guy. So if I want to do a resonance structure here, what pi bond am I going to break between which 2 carbons?
either
It's only have one choice. Which pi bond?
2 and 3?
Between 2 and 3. So that means this electron's going here, one's going there, and then the other electron's going to carbon 3. So let's draw that resonance structure. One, two, three, and 6. And then if this guy, of course, is going to react with Cl dot.
And now it's going to be
And where's the chlorine going to end on this one? On carbon 3. So here's one product. I'm going to try to draw it here. Cl.
That's product number 2.
That's product number 2. 1, 2, 3, 4, 5, 6. So there's product number 2.
Oh, I get it.
But now what about this guy?
Now,
Can I draw another resonance structure?
yeah.
Right, this is why numbering your carbons becomes really important. And it is different than the first one. Some people might say, oh, that looks exactly the same as the first one. No, it's different. 1, 2, 3, 4, 5, 6. So now when this reacts with chlorine, where is the chlorine going to end up on which carbon?
2. No, 5.
5. All right, so when Cl dot comes, five, 6. Can I do any? Are there any more resonance forms I can draw with this? I'm stuck, right? I can't. I can go back. I can go back this way, but that's the way I came from, so it's not going to change anything. So for how many different types of intermediates you have, that's how many different types of products you can form, right? So for this one, you have 3 different intermediates that lead to 3 different products are possible. Do
Let's keep everything how it is.
number 10, right?
Good job.
No.
Another one like it, NBS.
Oh, yeah, it's just like it.
So again, this is a complicated one because it's saying bromination of an alkene by NBS in the presence of light or peroxide is a radical reaction produces an allylic bromide, right? So this is going to abstract an allylic CH, right? So again, this is going to be really complicated now because we have how many types of allylic CHs here?
We had 2.
2 types, good. Is there one that's probably more likely to form than the other?
The tertiary one, because it's more substituted.
Probably. So let's number these carbons. So 1, 2, 3, 4, 5, 6. So 2 possible intermediates would be 2 and 5. So let's draw the radical here at 5. Can draw the radical here at 2. So one possibility would be to put the bromine on 2. One possibility here would put the bromine on 5. So we have 1 type, 2 types. So there's 2 products already. We haven't drawn a single resonance structure yet. So one thing we could do that would give us the dot here, which then could lead to having the bromine in this case on what was carbon 3. Right, after the resonance structure. We could also draw a resonance structure for this one. Now the radical's on 4. And that'll finally react. And put the dot there. So there's at least 4 products, it looks like to me. So the 2 different types of starting materials, right? There are two different starting intermediates, right? Where we took from 2 or 5, so 5 or 2. And the 2 products will lead from those. Then each of those can do a resonance structure, which would be a different product. So that's 1, 2, 3, 4. 4 types. So number 11.
He wants to know when he gets sad, he puts on together so it dances. That's what you're talking about. And it will be
This is good, this is good.
BR2 and heat, which would be the basically, so heat would do the same thing as like the light would do, right? It's gonna make the BR dot. Woo. Philosophical. Light is heat. Heat is light. Can be. So again here, so we got to figure out which we're going to take away an H, right? We're gonna do a substitution.
Heat is the same as HV.
Heat is the same as HV. Yep.
Okay. This is my-
So making BR dot. Which H are we going to take away?
Tertiary.
So I'll number the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Where's the CH we're taking away from which carbon? 2, I think. That's right. So we'd have BR dot. Have an H.
It's a vicious cycle.
In the initiation, of course, we made 2 BR dots. So the other BR dot comes in. That was a propagation step. This will be a termination step. And that's what we get. So you gotta be careful. The biggest thing you gotta be careful with, I think some people think I can abstract a methyl. No, you only substitute an H with these. You don't remove a methyl. Don't lose a carbon. Also remember, if you have a radical, you're gonna get both enantiomers in this situation too.
Yeah.